Unifying quantum mechanics and general relativity, a theory of everything. The quest for a unified theory, how an entangled atomic clock experiment could finally shed light on quantum mechanics and general relativity. One of the most daunting challenges in modern physics is reconciling quantum mechanics and general relativity. A groundbreaking experiment might finally offer some clues. In the realm of physics, quantum mechanics and general relativity are two of the most successful theories ever devised. Quantum mechanics provides our best understanding of the universe at atomic and subatomic scales, while general relativity, first proposed by Albert Einstein in 1915, offers our best understanding of gravity. According to general relativity, gravity is not a force, but the result of the curvature of spacetime around matter. But here's where things get tricky. Quantum mechanics and general relativity don't play well together. This incompatibility has puzzled physicists for decades as they strive to develop a unified theory that can explain the behavior of the universe at all scales. The problem lies in the fact that quantum mechanics and general relativity are based on fundamentally different principles. Quantum mechanics relies on the idea that particles are not point-like objects, but waves of matter, while general relativity describes gravity as the curvature of spacetime. These two concepts are difficult to reconcile, and attempts to combine them have led to mathematical inconsistencies and physical paradoxes. Testing precisely how spacetime curvature affects quantum mechanics could help us to unite the two theories. But designing such an experiment is challenging, primarily because gravity is much weaker than the other three fundamental forces. However, a new experiment involving a network of entangled atomic clocks could finally help us test how quantum mechanics fits with general relativity. The idea is to use entangled atomic clocks placed a kilometer apart. While they are in superposition, the clocks would experience different time flows, the result of being at different positions relative to Earth's gravitational field, potentially allowing us our first glimpse of how quantum mechanics and curved spacetime work together. While this is currently just a proposal, conducting the experiment could be a huge step towards unifying quantum mechanics and general relativity. We fundamentally do not know how to do this yet, so the results, if the experiment is performed, would be a huge boon for physics. So, what do you think? Could this experiment finally provide the clues we need to develop a unified theory of everything, or will it lead to more questions than answers? Let us know your thoughts in the comments below. This quantum clock experiment could revolutionize physics. A groundbreaking quantum experiment might challenge our entire understanding of time and gravity. Imagine 3 microscopic atomic clocks, each smaller than a grain of sand, suspended at different heights around a city, yet somehow connected in ways that defy classical physics. This isn't just any timekeeping device. These are quantum clocks that exist in multiple states at once, linked by a phenomenon Einstein famously called spooky action at a distance. Researchers are now proposing a radical test, using these interconnected clocks to uncover how quantum mechanics behaves in the warped fabric of spacetime, where Einstein's theory of gravity reigns supreme. But here's where it gets controversial. What happens when the strange rules of quantum mechanics, like superposition and entanglement, collide with the rigid framework of relativity? Scientists from the University of Illinois, Harvard, and other institutions are daring to answer this question with a bold experiment that could redefine our understanding of reality. Their study, published in KRX Quantum, aims to either confirm that quantum mechanics holds up under gravity's influence or reveal that our current theories are incomplete. How does this work? The experiment hinges on a principle Einstein discovered. Gravity slows time in stronger fields, a phenomenon known as gravitational time dilation. By placing 3 quantum clocks at varying elevations, about a kilometer apart, researchers hope to detect how Earth's gravity subtly alters quantum interference patterns. The clocks, made from ytterbium-171 atoms, will be trapped in optical cavities and entangled through quantum links, creating a W state where their states are intertwined across 3 locations. This setup could amplify tiny effects caused by gravity, revealing how quantum rules behave in a relativistic world. The team is targeting 3 core questions. Does quantum mechanics remain linear and unitary under gravity? Do the probabilistic rules of the Born rule still apply? And does quantum interference persist in curved spacetime? If gravity disrupts these principles, it could signal a fundamental flaw in our understanding of physics. Even if the results align with predictions, the experiment would be the first direct test of quantum behavior in this extreme environment. Technical hurdles loom large. Maintaining quantum coherence, where particles retain their delicate quantum state, for 50 seconds is a monumental task. Current atomic clocks achieve about 30 seconds of stability, but improvements are needed. Environmental factors like vibrations, magnetic fields, and temperature fluctuations could mask the experiment's subtle signals. Even positioning one clock atop the skyscraper introduces new challenges, as structural movements might interfere with measurements. Yet, the implications stretch far beyond Earth. If successful, this experiment could pave the way for future quantum networks linking satellites, enabling unprecedented studies of black holes, neutron stars, and other cosmic phenomena. It might even help test theories of quantum gravity, hypothetical frameworks that aim to unify quantum mechanics with general relativity. And this is the part most people miss. The experiment isn't just about time. It's about the very nature of reality. If gravity alters quantum rules, it could mean that our universe operates under different laws than we've ever imagined. But if the results match expectations, it would reinforce our current models. Either way, the experiment pushes the boundaries of what we know. So what do you think? Could gravity fundamentally change how quantum mechanics works? Or is our understanding of physics already complete? Share your thoughts in the comments below, because the answers to these questions could reshape everything we know about the cosmos. Exploring quantum theory in curved spacetime, a breakthrough experiment. What if the fabric of reality itself is built on tiny, indivisible units? This question sits at the heart of one of physics' most tantalizing mysteries: how to reconcile the quantum world with Einstein's theory of gravity. For a century, quantum theory has dominated our understanding of the microscopic realm, while general relativity explains the cosmos on a grand scale. Yet these 2 pillars of modern science refuse to merge seamlessly. The clash between quantum discreteness and the smooth, continuous nature of spacetime isn't just a technical hurdle. It's a philosophical dead end. But here's where it gets controversial. Some scientists argue that spacetime might have its own quantum structure, while others insist gravity simply doesn't belong in the quantum club. Now, a groundbreaking proposal by Jacob Covey and his team at the University of Illinois Urbana-Champaign could finally give us a way to test these ideas. And this is the part most people miss. Their experiment hinges on something as humble as atomic clocks, reimagined as tools to probe the very geometry of the universe. At the center of this debate lies the quest for quantum gravity, a theory that would unify quantum mechanics and general relativity. For decades, this has been a purely theoretical playground, filled with string theory, loop quantum gravity, and other abstract frameworks. But recent advances in quantum technology are shifting the game. Covey's team is leveraging cutting-edge techniques in quantum optics and gravitational interferometry to design an experiment that could, for the first time, observe quantum phenomena in Earth's warped spacetime. Imagine using a single atomic clock, split across 3 locations, kilometers apart, each at different elevations. By entangling these systems into a collective quantum state, the researchers can measure how space-time curvature, dictated by Earth's gravity, impacts quantum probabilities. This isn't just clever physics. It's a direct confrontation with the limits of our current theories. The experiment's brilliance lies in its simplicity and ambition. By encoding the clock's presence or absence into entangled atomic systems, the team creates the quantum probe sensitive to minute differences in proper time, the time experienced by each system due to gravitational time dilation. These differences, though tiny, could reveal whether quantum theory holds in curved spacetime or if gravity introduces deviations in probability calculations governed by the Born rule. The Born rule, a cornerstone of quantum mechanics, assumes probabilities are quadratic, something that breaks down in higher-order interference scenarios. But what if gravity forces new rules? Covey's proposal dares to ask that question, challenging the assumption that quantum theory is immune to spacetime's geometry. Yet the path forward is anything but easy. Maintaining the fragile entangled state over kilometer-scale distances is a feat that pushes the boundaries of current technology. Similar challenges plague other quantum gravity experiments, from detecting gravitationally induced entanglement to spotting quantum fluctuations in spacetime. The stakes are high. The Born rule has never been rigorously tested in gravitational settings, leaving a gaping hole in our understanding. Could future experiments expose cracks in quantum theory's foundation? Or will they confirm its resilience in the face of gravity's warping influence? The answers could redefine physics or upend it entirely. What's next for this field? Covey's work is just one thread in a tapestry of efforts to bridge the quantum classical divide. As experimentalists refine techniques to stabilize entangled states and theorists refine models of quantum spacetime, we may soon witness the first empirical evidence of quantum gravity's effects. But the bigger question remains: should we even expect quantum theory to survive intact in the presence of gravity? Some physicists argue that gravity's classical nature might render quantization unnecessary. Others see this as a red herring. Where do you stand? Drop your thoughts in the comments. This is the kind of debate that shapes the future of science.